Thank you very much. Thank you very much for the invitation. It's great to talk to you. And yeah, so this is a survey of joint work with Federico Binda. Some of it is still ongoing, but I will get it to the end. And it's a story about Brauer groups of schemes. So our setup is we start with some algebraic varieties, typically, and we are interested in this object that is called cohomological Brauer group. It's the second étale cohomology group of GM. And it is a very fundamental and basic invariant of the schema that has been used in the past in very concrete situations. For instance, it can be used to measure obstruction for local to global principle for existence of rational points. And it is also a birational invariant that has found a success in the past, providing the first example of unirational varieties that are not rational. So it's a great invariant, and we would like to know a little bit more about that. And the first time you encounter it, you might wonder, okay, how do we deal with this? I mean, it's an étale cohomology group, so it's typically difficult to grasp. And this question was asked by Grothendieck when he first introduced this invariant. And the fundamental idea was to look at the following table. It's an analogy table. So here we look at Hn et al. And we look for some concrete interpretation of cohomology classes there in terms of more understandable objects. So when n is equal to 0, H0, x, gm are just functions that are non-zero everywhere. So these are invertible functions. When n equal 1, we get the H1 et al. X GM, and it's a very standard fact in algebraic geometry that this gives the Picard group. So these are line bundles. And to keep some leitmotif that is important for this talk is that here there is the word invertible, and here line bundles are invertible sheaves. And then when we pass to n equal 2, what Grothendieck did back in the 60s was to introduce a notion of sheaf of Azumaya algebra that is not an invertible object in any concrete sense at the time, but somehow it was hinting at a good way to prolong this table. But the technology was missing back then. And today, thanks to the work of Bertrand Toën, we can see that the correct analogy to keep on this table is not to look just at Azumaya algebras, but we need to put this derived adjective in front of it. And then we can reinterpret them as invertible sheaves of categories. So there is some sort of categorification process that goes on from functions to sheaves, from sheaves to categories. So we are categorifying more and more. And the goal, so this is by now standard technology in the field. I will review it. I'm not assuming that you know this kind of things. But the goal of this work that I'm serving is fits in this context. And the point is we want to exploit Toën's viewpoint to get better knowledge, new results, better understanding of the Brauer group. And we have two main applications written down in the paper that I cited at the beginning, this archive. One is to a formal Gaga kind of situation. I will discuss it later on. And another one is to the Beauville-Laszlo kind of situation that I also discuss later on. This is what we were originally interested in because it leads to a larger program that I will discuss briefly at the end. Okay, so this is the general setup, and the plan of the talk is like this. So I will start by giving you a review of Azumaya algebras and derived Azumaya algebras. Then I will review a little bit of the categorical techniques, and then I will discuss the two main applications. Are there any questions before I get into it?
I'm just curious, what happens with the geometry? Is there a geometrical meaning of this cohomology in dimension n?
Higher dimension.
Higher, yeah.
So it gets, it gets harder and harder. you need to categorify more. Like you need to go to 2 categories, 3 categories, but it gets more and more difficult, and the technology is not ready. I mean, we are not ready to deal with this kind of stuff. So it's a natural thing. This table, especially after the work of Toën, we kind of understand the logic behind how to get to higher groups, but from a technological point of view, it's very demanding, very heavy. Somehow this thing is we have a good by now we have a good technology that allows to treat it in a concrete way without getting mad about categorical details. But going higher, for now, the technology requires getting mad at categorical details, which we don't want to do. And unless we are pushed by some concrete need from algebraic geometry, I don't think we will do it. But maybe one day we will have a question that really requires this, and then someone will do it. Okay, so Azumaya algebras. Let me start from a classical setup. So we have a schema, and we have a sheaf of Azumaya algebras. What is that? So a sheaf of Azumaya algebras is a pair where Vm, where V is a vector bundle, and M is a multiplication, OX linear multiplication. It's not commutative, typically, just associative. And we ask a certain important property, which is that this map going from V tensor V op is just V endowed with opposite multiplication to this endomorphism of V, the endomorphism sheaves, given by this conjugation map, should be an isomorphism. So here I'm using the multiplication of the, this is the Azumaya multiplication. And so you see that it's something that really depends on the product, not just on the vector bundle. Particularly here, there is no V duo. It's really V just endowed with the multiplication, the opposite multiplication. So this is a sheaf of Azumaya algebras, and there is an together with this notion, we also needed the notion like how we identify Azumaya algebras, and so. 2 sheaves of Azumaya algebras are Morita equivalent. This is the good notion to look at. If there is an OX linear equivalence of categories between modules. So we look at modules for A1, modules for A2, and we want to have an abstract OX linear equivalence between these 2 categories. I will show an example later on. Let me give first general examples for this definition. So, okay, the most trivial one is that the structure sheaf is Azumaya. If you want to see some non-trivial example, this should do. So we fix some pair of numbers, and we fix a prime such that the Hilbert symbol of AB at the prime is 1. So this Diophantine equation has some non-trivial solution. And we work over ZP, localized at P. And then we can just write one quaternionic algebra. These are like quaternionic relations, and one can check that this is indeed an Azumaya algebra. So this is an Azumaya algebra. It's not associative. So these objects exist, and to get a feeling for what this Morita equivalent means, well, you should think that A is trivial, Morita equivalent to OX, if and only if it's isomorphic to a matrix algebra. So when we look at matrix algebras, the category of modules doesn't change. Standard fact, I mean, important fact in K-theory. Sorry, I want to there. It's equivalent to modules over OX. And so this is what it means to be trivial. It's an endomorphism of. So this also means that it's isomorphic as algebra to endomorphism of OX power n by composition. Okay, so these are examples. Matrix algebras all give examples, but they are all trivial. And then there are some non-trivial examples. And we use the following notation. So the Brauer Azumaya group is the set of Azumaya algebras quotiented by Morita equivalence relation. We have a natural extra operation on this group, which is tensoring to Azumaya algebra. A tensor B is still Azumaya. If A and B are. And so we get a group, which is the Brauer-Azumaya group. And now we will discuss how it relates to the other one. So before discussing the relation, let's see another example. We have, by definition of the projective general linear group, we have this short exact sequence of étale sheaves over any scheme. And then we can pass to long exact sequence of cohomology, and we get a boundary map that goes from H1 PGLN to H2 et al. GM. And so we see that any torsor for this algebraic group gives rise to a class in the Brauer group. And we will see that, we will see it is a fact that this boundary map actually produces Azumaya algebras in this sense, in the sense of this definition. And now the relation between these two groups and other facts that are useful to know about this kind of stuff is that, first of all, every Azumaya algebra étale locally is a matrix algebra. So étale locally, we can trivialize every Azumaya algebra. So you can think of Azumaya algebra. Sometimes people say that Azumaya algebras are twisted form of matrix algebras. So locally, they look like matrix algebras, but they glue up in a non-trivial way, just like vector bundles glue up in non-trivial way starting from trivial bundles. There exists an injective map that goes from the Brauer-Azumaya into the Brauer. It's injective, and natural question is about surjectivity. So what can we say about surjectivity? We can say that it's not surjective typically. First, the image of this map is included in the torsion part. So whatever comes from a classical Azumaya algebra will be torsion with respect to the operation in the Brauer group. And second thing is that there is a famous example of Mumford where he constructed a normal surface that is not regular, such that there are many classes in the Brauer group that are not torsion. So in the end, if you put all these things together, you get that typically when the scheme is not smooth, for instance, you expect to have classes in the Brauer group that are not representable by Azumaya algebras because they will not be torsion. And now, this was the state of the art until 2012, but then Toën proved this result, which is every class in the Brauer group is actually representable by a derived Azumaya algebra. And so the point is that if we change a little bit and we allow for this adjective derived, then everything gets representable. And so we get, let's say, full understanding of classes there in terms of somehow more concrete objects. And maybe let me make a remark about this point. So remark is that, for instance, knowing that this works is great because we know how to manipulate line bundles. And so this side is extremely more concrete. So we know what to do. We know what is the relevance for line bundles, how to use them, how to prove things about them. While on the other side, we just had an abstract cohomological group, which we don't know much about. So in the same spirit, if we go back to the definition of Azumaya algebra, an Azumaya algebra is somehow a concrete object. It's just a vector bundle, which we understand very well, together with a multiplication that has some nice properties. So you can easily imagine to do concrete things with this kind of objects that you wouldn't know how to do with an abstract class in the H2 et al. GM. And so whenever we have a class there, we are interested in understanding, and we know that it comes from there, we are happy because we get some more concrete feeling about this class. And so this theorem is really great because it surpasses a limitation of the theory by just modifying some adjective. And now let me give a definition of what is derived Azumaya algebra to get a feeling what is the difference with the classical picture. So again, we have some scheme, and we have a sheaf of derived Azumaya algebra now is a perfect complex. So instead of having a vector bundle, a single vector bundle, we have now a complex of vector bundles like this, bounded. At some point, it gets to 0. So this is an object in perfect complexes. And let me call it V bullet. And again, we want a multiplication, V tensor V, that goes to V, associative multiplication in complexes of vector bundles. And now we have to ask two conditions. So the first condition might seem different from what I was saying before. What I was saying before is the first condition is that a V is a vector bundle. Here I'm asking that A is supported everywhere. Let me just do one example to clarify why we need this kind of hypothesis. Let's take X to be A1, and let's take V to be the complex KT, and multiplication by T. So this is a perfect complex on A1. However, when we look at its cohomologies, Hi of V, they are supported just on 0, because the only two cohomologies are H0 and H1, and H0 is K, the co-kernel of this map, and H1 is also K, which is the kernel of this map, and so it's supported. It's complete. Sorry, this map is injective, so the only thing is H0, and H0 is just K, which is supported on 0. And so this is a perfect complex, but it's not supported on the whole thing. While a vector bundle, we know it's supported everywhere. Its fiber at every point is non-zero. So the true analog of this first condition here, V is a vector bundle. When we allow V to be a perfect complex, it becomes V is supported everywhere. So this is a good analog of being a vector bundle. And the second condition is the same. We want that the canonical map is no longer an isomorphism, but it's a quasi-isomorphism. So it's an isomorphism at a level of each cohomology group. And so this is the definition. It's exactly the same kind of object. We just allow them to be complexes. And then we also have a definition of what it means to be derived equivalent and Morita equivalent, which is we have an equivalence between the category of DG modules, because now our algebras are complexes. So when we look at modules for these algebras, we look at modules that are complexes themselves, so DG modules. And we want the same kind of thing, an abstract equivalence. Okay, so this is the definition. Before getting into discussing like objects of this form, let me remark that if we put together Toën's theorem and the Mumford example, so we know forcibly that there must be some derived Azumaya algebras that are not classical Azumaya. Classical Azumaya algebra give rise to things like this. That's easy. But more importantly, here we have something more that comes by, I mean, if you believe to this theorem, it must exist. And now the point is that it's somehow contrary to what happens in the classical situation. It's kind of difficult to give explicit examples. I mean, to actually give a bounded complex together with an explicit multiplication that makes an Azumaya algebra. So I cannot give you something like this. I mean, I'm not able to. So how can we control these kind of objects? How can we construct them in explicit? How can we be sure they exist? And the point is that actually Toën provides a different definition, a different construction of Azumaya algebra that turns out to be equivalent by a non-trivial theorem to this one, but it is more categorified in nature. And this categorified point of view, it produces objects that are easier to construct and easier to manipulate and so on. And so this is what I'm gonna do now, review this categorified viewpoint. But before getting into that, let me just fix the notation. I will use the derived Brauer group to be derived Azumaya algebras up to derived Morita equivalence, which is exactly the same definition of the Brauer group we gave before. And so in these terms, we could write a corollary due to Toën, which is that there exists a canonical surjective map from the derived Brauer group to the classical Brauer group. In most cases, this map is an isomorphism, but we'll see later. Okay, are there questions about these things before I move to the categorical?
Yeah, I wanted, maybe this is like really basic, but what's the DG like modules? What's the DG?
Yeah. So just think. So if I write like this, chain complexes of OX. So these are chain complexes in OX modules, or in quasi-co, let's say. Okay, so these are chain complexes of quasi-coherent sheaves. And now the algebra A1, you should think of it as an algebra object in chain complexes OX. So it is a chain complex that has a multiplication as a chain complex. For a concrete example, take again the Koszul resolution, KT, multiplication by T. This is a complex, and it has a multiplication. The multiplication, when you multiply an element of this degree with itself, you still get an element in this degree. When you multiply an element here with an element there, you get an element there with the usual multiplication of polynomials. And when you multiply two elements there, you get something here which is 0. So the multiplication between two elements in degree 1 gets 0. And so this is a differential graded algebra. And this is what it means to be an algebra in complexes. And now, because we have an algebra in complexes, we can also look at modules for A1, but in this category of complexes. Okay, and now this is an abelian category, but when I invert quasi-isomorphism, then I get what I call DG modules. So this is some sort of derived category, but done not with respect to OX, but with respect to this twisted form of OX.
Okay, thank you.
Okay. More questions? So maybe the whole point is that using these kind of homotopical techniques, I mean, when I say homotopical techniques, I mean dealing with chain complexes instead of vector bundles, instead of sets. We allow things that have some homotopy dimension. And the advantage of doing this is that something that you couldn't represent in any concrete way becomes representable now by allowing your algebra to be a complex.
Can you say again? How does this corollary follow from the previous thing? I mean, the surgical map from D Brauer group to Brauer group.
I'm not sure I understood the question. Can you repeat?
Sorry, just now you mentioned about a corollary. There exists a canonical surgical map from the derived Brauer group to Brauer group.
Yes.
I don't see how does it follow.
Oh no, it's it's highly non-trivial.
Oh. Okay,
it follows from this theorem.
Okay.
I can say a little bit more. Actually, it turns out that this derived this is a theorem that the derived Brauer group can actually be computed as the sum of H2 et al. X GM plus H1 et al. X Z. And this extra term is 0 if X is normal, for instance. And in this case, so this map is comes from this identification by projection. But of course, the definition I gave makes not clear at all why this isomorphism exists. And it really it's really one of the main theorems of Toën that this thing exists. Of that.
Okay. Thing. Yeah, no problem. I just I was thinking I missed something you said.
No, it's a good remark. Yeah, no, it's it's a non-trivial point.
Okay.
Okay. So now let me change a little bit perspective. So I need to categorify, and when I categorify, I increase a little bit the level of generality. And so here I was working with the categories like localized, derived categories. So maybe triangulated categories. And in order to make all these things work, we need something a little bit more strong than triangulated categories. So we will be working with infinity categories. You can think of triangulated categories, but better. Okay, and I need to set up some terminology. So I will be using a PRL omega. So these are presentable infinity categories. If you don't know what they are, just think of presentable means describable as via generators and relations. So let me give an explicit example. You take some topological space and you look at pre-sheaves of X and you look at sheaves on X. So you think of pre-sheaves as a free category. And this, it's a quotient by the sheafification functor of a free category. And so presentable categories are essentially what finitely presentable modules are with respect to all modules somehow. The pre-sheaves are free, and then we look at the quotients of them by localizations, and we get what I call presentable. Anyway, we also ask to be generated by compact objects. This is a harmless condition in most cases. Typical example is mod A, and it is generated by A itself. And we look at, we keep track of morphisms that are left adjoints and that preserve compact object. And this is technical, but I need it, otherwise everything else doesn't make sense. And now, one great bit of technology that has been developed in the last 20 years by people like Lurie, for instance, is one notion of tensor product of categories. And the definition is somehow very similar to what you would expect from the tensor product. It is the thing that represents functors that are continuous in both variables. So here I'm looking at functors from C times D to E, such that for every C, the induced functor commutes with colimit, and for every D, FD commutes with colimits. So this is the analog of functions that are bilinear. Function that are bilinear becomes functors that are bicontinuous. And it turns out that this thing is co-representable by a tensor product of categories. And then this tensor product, we can compute it, we can control it. Probably doesn't tell you much written like this, but let me give some example to forge your intuition about what this language subsumes. So if we look at some pre-sheaf category and we do tensor product, we just get pre-sheaf on the product of the two things. So like if we have some two topological spaces, let's say, then pre-sheaves on them are just the tensor product of the two pre-sheaves are just pre-sheaves on the product. And another important thing is that is this: if we look at sheaves on some topological space, tensor with some category of modules, we get just sheaves with coefficients in mod A. And so the functoriality of this construction, it's great to deduce properties for this category that we might care about out of abstract properties of just sheaves. So passing from set to whatever you want to enrich your sheaves with. So these are like the rules of the tensor product that allow to compute it in most cases, let's say. And then to get some feeling of what is this tensor product is saying, well, you can look at things like commutative algebras in presentable categories. So here I would be looking at things like a category together with a map, which is a functor from C to C. And this functor, let me call it M. And because because the tensor product means this thing, actually we can think of this M as some tensor product, tensor structure for C that commutes with colimits in both variables. So the thing that I wrote here. Let's see one basic example before 4. It's we look at mod A. So this is a category. It's presentable, and we have the tensor product over A that goes from mod A times mod A to mod A. It's just a tensor product over A, and it's bicontinuous, commutes with colimits in both variables. So we get an easy example of something there. And this can be generalized if we take some quasi-compact, quasi-separated schema, then the derived category of X is a commutative algebra object in PRL omega. And so this is our basic, let's say, setup. And you should think of this dx together with its tensor. The operation is the tensor product of quasi-coherent sheaves, complexes of quasi-coherent sheaves. And this categorifies OX, the structure sheaf. So when we are going up at the categorical level, functions become sheaves, sheaves become categories. So OX was a sheaf, it becomes a category, the whole category, derived category of quasi-coherent sheaves. Okay, and we give this definition: quasi-compact, quasi-separated schema. Categorical quasi-coherent sheaves are modules in PRL omega for this thing. So things dx that x on module structure. Let's see some example. This is a very general definition and it includes most things you know. So as I was saying, the action of the x is the categorification of the action of OX. To see examples, let's just take a map of schemes, Y to X. Then by pullback, we can tensor any sheaf on X with a sheaf on Y. So here, if I have to write explicitly the operation that I'm talking about that gives the module structure, it's like this. We take some sheaf on X, we take some sheaf on Y, and we send it to LF upper star of F, tensor over OY with G. And so this gives a module structure. And so basically all schemes gives rise to a module via the derived category over X. It inherits an action of X. And this maybe this thing you should think of as the categorification of RF lower star of OY. And then a general remark is that I am actually a little bit cheating, but it's the only way to keep the talk self-contained. I'm cheating in the sense that it's not clear why this definition I gave has anything to do with sheaves, but it's true. There are a couple of important theorems in this area that essentially guarantee that this definition is a good definition. And so in particular, the terminology is also justified. We can think of objects there as sheaves in some sense, but I will not get into the details because it's not needed for what follows. Okay, so I know it's a lot to digest, but the whole point why I'm doing this is to give you some mind-blowing coming back to reality. So this is the main thing of Toën in his paper. We start with some quasi-compact, quasi-separated scheme. We give these two definitions. So derived Azumaya categorical is the full subcategory of these categorical sheaves spanned by tensor invertible objects. So you see the analogy with the pick X inside quasi-co-X tensor invertible sheaves. And now we categorify, and then here we get PRL omega X. So this is categorical level. And the same thing inside, we call it Azumaya, derived Azumaya cut. Not clear why it has something to do with Azumaya, but it comes from the theorem. And then this was a category. We want a groupoid, so we just take the maximal groupoid inside. So we throw away every morphism that is not an equivalence. And then the theorem is the following. This thing I defined, derived Azumaya, is a simplicial set. And so we can look at its homotopy groups. And here's the point. Its connected components are exactly the derived Brauer group, and it's exactly this decomposition. Actually, this identification here comes from the analysis of these connected components. The pi1 of this topological space, it's the derived Picard, which is essentially this product, H1 et al., and then there is Z. Derived Picard, you should think of this component as given by the shift. So here there is a line bundle, and here there is a shift functor for the derived category. The pi2 is just invertible functions, and there are no higher homotopy groups. So we only have 3, pi 0, pi 1, and pi 2, and we get back exactly the table I wrote at the beginning. And so, okay, we use some high technology, but in the end, we got back the objects we cared about. And so now the question is, how can we hope to use these kind of results to improve our knowledge about Brauer groups? And so I want to give 2 examples. And the first, so both are very concrete and very easy to state. So I just need some terminology, some notation to set up the problem. So let's take some complete local ring. Think of power series, for instance. We take some proper scheme over S. So this is an infinitesimal family of schemes varying over this base. Sn is all the infinitesimal thickenings, and the xn is the base change. And then I need to look at the formal completion of X at the special fiber for technical reasons. So this is should be a familiar situation when we study deformation theory. For instance, it's something that pops up all the time. And the Grothendieck existence theorem, one way to state it is that we have this equivalence. In order to know an étale cohomology for the H1 class H1 GM, it's enough to know it after each reduction. And we can glue it together to construct a line bundle. So another way to state this is Picard of X is limit of Picard of Xn. This is essentially saying that if you have a line bundle over the central fiber, you can lift it to the whole family, provided that you know how to lift it step by step. Okay, so this is a classical result, and the question is, what can we say, what can be said about the H2? This is a classical question that arose essentially as soon as these kind of groups were considered by Grothendieck himself, that prove some results. And so here's the best result proven by Grothendieck, which is more or less the best result that was known before we started working on this topic. So first, not a random local complete ring, but a DVR. That's fine. We need assumptions on X. We need X to be regular, and we need it to be flat over S. And we need this map, this X assumption. The lim1 of peak Xn is 0. If you don't know what is a lim1, it's this. You have the infinite product of Xn, infinite product repeated. And here you have a map that sends a sequence ln to the sequence ln minus ln plus 1 restricted to Xn. So when you take the kernel of this map, you get exactly the limit, which means families of line bundles, such that when I restrict ln plus 1 to ln, I get ln. This is the limit, and it's also peak. And the co-kernel of this map, it's by definition the lim1. And so to get a feeling for when does this thing is 0, when is this thing 0, when does this thing vanish? Essentially, if there is no obstruction to lift line bundles, whenever you have a line bundle at level n, you can lift it to level n plus 1, no matter what line bundle you started with, then this lim1 will be 0. But it's a very strong condition. In typical examples, it's not true. I mean, it's very, very rare. There are, of course, examples, but very, very rare. Then what happens is that the canonical comparison map is injected. So this is what was known. And now we can improve this result in the following way. So before I was talking about the formal completion of X along its special fiber, can define its second cohomology group as the H2 of this limit So these are complexes. So I'm taking the limit of complexes, and only after having taken the limit, I take the H2. I need it. And then the theorem is greatly simplified. So first, we don't need a DVR, just complete local ring, and we don't need any regularity, and we don't need any flatness, just a proper scheme of S. And then we can prove the following. The canonical, this comparison map to the formal completion is always injective, and we have a short exact sequence of this form. So if we put the two things together, you see that here you have this map that injects there. And this composite map is the target map. And so you see that because this is always injective, as soon as this group vanish, this map is also injective. And then you get back a Grothendieck result about the injectivity of this map. But this result is finer, and there are in particular situations where this group is non-zero, and one can control the injectivity of this map via this diagram. We worked them out in the paper. There are some examples where this happens. And so it sheds some light. And the whole point is that how did we get this result? How do we prove this, in particular, this injectivity, which is the most important part, because the second part is kind of formal, just out of the definition, but this one is non-trivial. And the point is that we prove it by categorifying. And the actual theorem is the following. We look at categorical sheaves. We look at categorical sheaves. We look at the canonical comparison map, but at the categorified level. And we prove a fully faithfulness statement restricted on dualizable objects. I didn't say what they are, but the important thing is that invertible objects are inside. And so Azumaya algebras are inside. Objects are inside, and these are Azumaya. And so we actually prove something more general at the categorical level. It's actually easier to prove. And then we deduce a general statement about the Brauer group. This theorem has a funny application. It's the following. So always the same setting. We look at some GM gerb. So GM gerb means that locally A is of the form X times BGM. Locally, et al. Locally. And in particular, the canonical map to X is not proper. Cannot be proper because GM is not proper. So the classical Grothendieck existence theorem does not apply for this group, for this scheme A. And so we could look at this canonical comparison map, but a priori there is no reason to believe that it's an equivalence, but it actually follows from this theorem that it is an equivalence. So this fits in some line of research that has been pushed by Reed and all, but it goes beyond what was known in the literature. So combining results of various people, we knew that this theorem holds when A is simple, is a global quotient. But when A is not a global quotient, and there are many examples of those, we didn't know about Grothendieck existence theorem. We can deduce it out of this theorem as a formal consequence. Okay, so this is the first kind of application I had in mind, and I think I have maybe 10 minutes because I started at 11:04.
Yeah. Don't worry. 10 minutes.
Do you have questions before I move on?
I think so far it's okay. Nobody said anything in the chat. So.
Okay. And so it will be a little bit faster. So the Beauville-Laszlo setup, Beauville-Laszlo theorem, is the following statement. So I will just state the simplest version. I take some Noetherian commutative ring, and I take some ideal. And I look at this diagram. So here I have spec A, S. Here I have the formal completion at the ideal. Here I have the open complementary of the zero locus of the ideal. And then I have the pullback, which is the complement of, the induced ideal. I take a zero locus on the formal completion and I remove it. So if we look at a very concrete example, we take A1, so polynomials. The ideal is just T. And then what we have is CT. We have a formal power series. We have polynomials that are non-zero. I mean, we allow T to be at the denominator, and then Laurent power series. And from a geometric point of view, maybe I can draw a picture. So this is A1. Then we have some fat point here, which is the formal completion at 0. Then we have a GM. And here we have the fat point, but punctured. So A1, 0 minus 0. So this is what this picture looks like in geometric terms. And if you think in very differential geometric terms, you expect to be able to construct sheaves on this thing, knowing sheaf on the open, sheaf on the fat point, with a gluing datum on the punctured tick point. If you think of this as a tubular neighborhood, I mean, some tubular neighborhood, then in thinking topological or differential geometric terms, then it's clear. And in algebraic geometry, it's a little bit more challenging to formulate it. But the Beauville-Laszlo theorem states exactly this, that the derived category of quasi-coherent sheaves on S can be reconstructed as a fiber product of derived category here, derived category there, and derived category here. So Beauville-Laszlo proved it for vector bundles. So this is saying, for instance, that vector bundles on CT can be written as vector bundles on formal power series, vector bundles on Laurent, and vector bundles on TT minus 1. And this statement, maybe let me say, it plays a really important role in geometric Langland, for instance. It's a basic statement, but it's really useful. Okay, and so the goal, the second result that we prove in this paper is that this same result holds at the categorified level, where we replace the derived category of quasi-coherent sheaves with categorical sheaves, and then we get an equivalence of categories. And maybe one remark is that fully faithfulness is easy, but essential subjectivity is somehow surprising, let's say. And indeed, in the formal Gaga kind of statement, here I wasn't saying anything about the subjectivity of this map. I was talking about full faithfulness. We know that this map cannot be fully faithful, cannot be essentially subjective, exactly as we know in the theorem of Grothendieck that this map that was injective cannot be subjective. There are explicit examples that prevent subjectivity. If you start adding hypotheses, maybe it becomes true. But at this level, it will become harder to prove subjectivity. And so you can see the analogy between the two statements. It's always about comparing something with a limit on the other side. And so here we know that it's fully faithful. So it's in line with what we proved in the formal Gaga kind of statement, but the essential surjectivity is proper to this situation, and it's the difficult part. Okay, and so why do we care about this kind of statements? So first, you can ask what kind of consequences can I get out of it, concrete consequence. The most concrete consequence is the existence of some long exact sequence for Brauer group that relates the Brauer group of the whole thing with the Brauer group of an open and the formal completion at the point. And it involves, so this map is typically not injective. We can find the obstruction in the Picard group of this V was the Laurent power series and so on. Okay, so these might be useful, might not be useful. It's an easy consequence, that's it. But the real reason why we cared about this statement, and the whole reason why we started writing the paper, was that we actually care about something a little bit more elaborated that is called the adelic descent. And so let me give some basic idea. And so to fix idea, let's just work with curves. So let's say that X is a curve. Then there is a theorem of a veil that says the following. Ban G of X can be written as a quotient of Ban G of the adel of X with a double quotient. Here there is G of the adel, and here is G of OX. And why this statement is nice? Well, the point is that this thing is completely decomposed. Completely decomposed in terms of formal completions at every point of X. So concretely, if you have a curve X, you are saying that to give a vector bundle or a G bundle on X, you only need to give a vector bundle on each formal completion. So every point you formally complete, but that's easy because it always gets to be like this. So it's a super local statement plus some gluing data. And so this is a great theorem of Weil that allowed for like deep studies of the topology of Ban-G passes through this theorem. Let's say like this. And so we would like to know something similar, but for Azumaya. And so what we would like to say is that derived Azumaya of X satisfies adelic descent. And we did, so this is the conjecture that we are trying to prove. And some concrete gain that one would get is the following. I just sketch the main idea. Well, one would get something like this. So this is some called valence on higher ADL. And in the case of a curve, you don't see them. When you have a surface, what is a higher ADL? It's not a formal completion at a point, but it's a formal completion at a flag. You first take a curve, then you take a point on the curve. You first take the formal completion at the curve, you puncture it, and then you recomplete the point that you had. And this is some iterated like higher local fields, something like C, T, S, something like this. There is this higher ADL kind of operation, and it kind of decomposes the surface or whatever schema you like in terms of very local data, in terms of formal completion of things. And what we would get is this kind of time relation like this that would induce a spectral sequence, which would be new, computing the Brauer group. And so in particular, we will get some new filtration on the Brauer group. And we did some experimental computation, let's say, for instance, in the surface, the Mumford surface, and we found that this new filtration is new, and it really separates the derived part from the underived part. So it has like a very, it gives some concrete control on this group. It allows for study it, and also when we get to sufficiently high dimension, I think it was from dimension 3 on, there is no reason for this spectral sequence to degenerate at the early stage. And so we get like a higher differentials that are like a very sophisticated map involving the classical Brauer group with other invariants. For low pages, we found a trace of all these maps in the literature, but starting from dimension 3, we couldn't find anything more in the existing literature about Brauer groups. So we are quite excited about seeing where all this story will bring us in the future. And that's it. Sorry for being over time.